Alright guys, so this is a 33 kilowatt or roughly 44 horsepower electric motor. This is specifically a spindle motor. More than likely this is probably used on some sort of CNC machine. There's not a lot of available space inside of these type of motors. They really pack these things in there. I've identified this connection as a one circuit Y delta. So this motor has 60 slots and it has groups of 3 coils and groups of 2 coils. So we have 6 groups of 2 and 6 groups of 3. While we're stripping this winding, we can actually find our fault right here. So we have a ground fault failure. You can see how these magnet wires are broken. And after we get the entire winding stripped out, you can actually see our big copper blob right here, right on our core stack. Now, sometimes you can just grind that copper out of there, but this is a pretty significant failure, and I'm not going to be able to remove all that without actually cutting that part of the stack out. So this core is made up of hundreds and hundreds, if not thousands, of laminated pieces. This isn't necessarily the method I would choose to do this in, but there's no replacing this core. We're not going to get this restacked, and this is, of course, as you know, a rush job. Now, the reason these stacks are laminated and made up of hundreds or thousands of individual pieces is so we can reduce eddy currents. We want to reduce those circulating eddy currents, so if we made this stack out of just a big solid piece of steel, we would essentially have a huge heater, not an electric motor. After we've sandblasted and insulated that core using a Nomex Mylar Nomex paper, we're going to go ahead and stuff all these coils in there, and we're going to separate all of our groups with phase paper. Remember that those different phase groups have a different potential, so we're trying to protect that voltage potential difference between those groups. As I said, they pack these things super tight. That winding cannot even be a little bit bigger than it used to be, otherwise that end bell's not going to fit over it. We're going to have to go ahead and duplicate and remake our same connection. Then we can run this thing through a couple different tests, so we'll put it on a winding analyzer, and then I'll go ahead and energize it without the rotor inside of it at a reduced voltage, and we'll just make sure that nothing's heating up unevenly, nothing's getting hot. And then we can do our old dummy rotor test. So we're actually applying some voltage to this, moving some current through it, and if we stick this aluminum can inside of that stator, we're going to start inducing current into that aluminum can, and it's going to rotate with our magnetic field. Once we've dotted all of our T's and crossed all of our I's, we can go ahead and actually assemble the thing, and we can test run it with the rotor in it. Now, it might not sound like it, but it is actually running right now, and this can run up to 8,000 RPM. Now, it is still running, so don't touch it, but if we look at the exterior casing of this, you can see the actual laminations of that stator stack. This outside isn't just a housing, that's the actual stator stack of this electric motor. Then finally, we can get everything assembled, put all of our shaft attachments back on, and we can throw this thing on a pallet and send it back to the customer. Now, some of you guys have asked, how do I get a job like this? Well, you go to the EASA website, EASA, that's Electrical Apparatus Service Association. You go to Find Active Members, you scroll down to a state that you want to work in, which in my case is Wisconsin. It'll pop up all these places that do electric motor repair work. Click on one, find their email, call them, say hire me, and tell them Keith sent you. Cheers.